Good morning, everyone. My name is Wilfredo Mendez. Most of the people heard of Zach, and I think that it Grenoble, where I work with Catherine Parr. So today I'm going to be talking about interfacial complexation, specifically interfacial complexation at an aqueous two-phase system. Now, aqueous two-phase systems are mostly just water-like systems that generate a liquid-liquid interface. So this schematic here on the left kind of shows you exactly the system working. What we're basically doing is we have both or bulk systems, and we add oppositely charged species, right? Polycation, which is a p-diatomac, and an anionic nanoparticle. The idea is that these two species will innately meet at the interface and assemble. So if we look at this, right, this video here on the top right, this is a pendant drop setup. And what you'll notice is that not only is my phase stabilized, my droplet phase with the charged polymers stabilized, but we get this very extensive, thick coacervate membrane forming towards our nanoparticle phase. So this video here is around 30 minutes, and these membranes keep assembling as time progresses. Now, they're pretty robust. We're actually also able to translate them to droplets, right, where you can clearly see this very noticeable coacervate membrane on the outer interface. Now, systems like this are extremely popular in literature, and that's basically because they have a huge, very wide, spectrum of applications that span from, filtration membranes to membraneless organelles. So even though this is really, really well studied and it's kind of a hot topic currently in literature, there's not many work pertaining to the mechanism of assembly for these membranes. That's basically where I come in, right? I want to answer is how are these membranes assembling? So to answer that question, we posit two hypotheses as to how these membranes are growing. All we know is that these systems are polymer mediated. Their growth is polymer mediated. And to kind of guide our thinking, what we did is we established these two growth schemes. The first growth scheme, we call it membrane penetration, is basically based on the idea of this polymer diffusion, where a polymer species is able to completely migrate to the leading front and complex. The second scheme is one that's more kinetic in nature, right? Where the binding, debinding interactions of your polymer are mediating transport of the polymer through the membrane. Now, both of these guys technically can explain what we're seeing, right? On the bulk assembly I showed you on the pendant drop. So to kind of distinguish between these, we need to, find an experimental setup to distinguish between them. And to do that, we basically translated our system into a microfluidic device. So this video here on the left shows you the assembly of these membranes as a function of time. So here we're growing for around 8 hours. As you can see, we're able to generate these very thick coacervate membranes growing towards our nanoparticle phase. So that membrane there is around 300 microns, right? So this is extremely thick, structures. So the question now is, how am I going to use this microfluidic device, this membrane, to distinguish between these two, growth schemes? So to do that, we basically take advantage of what is called sequential deposition. So this schematic here shows you the thinking that we're doing. The idea we thought about is what happens if we change our polymer populations. So let's say I grow a membrane with population 1, which is non-fluorescent. Then what would happen is I'll basically generate this, what we kind of describe here as this purple line. Now the question is, if I go ahead and I swap this polymer population for a different one that's fluorescent in nature, where will this fluorescent polymer locate itself in the membrane? So basically, I present two possibilities, right? It can either go to the leading front, where you can see the non-fluorescent band, fluorescent band, or the opposite. And if it's the opposite, then we're dealing with this complex partner swapping scheme or the membrane penetration. So this is a video of what actually happens. So what we did here is we actually did 3 insertion events from non-fluorescent to fluorescent, and then back to non-fluorescent. And what you'll see at the end of this video is that we end up with this sandwich-like structure between with non-fluorescent band, fluorescent band, and non-fluorescent band, basically showing us that the system is following this membrane penetration scheme, right? So this is pretty good. Other question we wanted to answer is, what is the ratio of our polymer to nanoparticle in these coacervate membranes? To kind of try and answer that question, what we did is we basically peeled these membranes, we broke them into pieces, and we did some TGA. And the idea here was to basically burn away all the polymer species and see how much the weight changes, as a function of temperature. What we're seeing is that we're losing around 50 to 40%. So these are really, really polymer-rich coacervate membranes are being built. And yeah, overall, I showed you that these systems are growing through this permeation first mechanism, right? We're seeing these 3-layer structured based on the insertion events from non-fluorescent, fluorescent to non-fluorescent. And this is huge, right? Because this basically gives us structural control over how our membranes are growing. And you can envision myriad of application. Key among them, like this target release system where we can, build different layers and release them at different inputs. And that's it.